Inlets are locations where water passes through barrier islands to the lagoon and vice versa. If barrier islands are the most dynamic and changeable of all depositional coastal features, inlets on barrier islands are the most dynamic and changeable places on barrier islands. This is definitely not the place where you should build a $10 million hotel and expect to be problem-free. Inlets are so dynamic because of sand, which flows into them and out of them on a daily basis. Sand is carried by two main processes. Number one, longshore drift, which creates a continuous movement of sand down the shore that can potentially clog or even close the inlet. And number two, tides, which force a large volume of water through the narrow inlet once or twice a day, depending on the type of tide. As the water is squeezed into the inlet, it accelerates and entrains lots of sediment, but when it reaches the other side, it slows down and deposits much of the sediment. The total amount of water passing through the inlet each tidal cycle is called the tidal prism, and generally correlates with the velocity and energy of the water as it moves through the inlet. Inlets with a large tidal prism generally have vigorous, energetic flow through the inlet, while inlets with low tidal prisms generally have sluggish tidal currents. The sudden slowing of water once it reaches the other side may produce two accumulations of sediment, one inside the inlet to the lagoon and one outside the inlet in the sea. The one in the sea is called the ebb tidal delta because it is caused by the outgoing or ebb tide. The one in the lagoon is less commonly seen and is called the flood tidal delta because it is caused by the incoming or flood tide. The critical zone, shown in yellow on this slide, is where sand moved by both processes collides, right in the outlet of the inlet. Sand moving via longshore drift can clog the inlet, while sand carrying currents caused by ebb tides can flush the inlet clear. The balance determines the two main types of inlets, but there are of course an infinite number of types between the two end members I'm going to describe next. Tide-dominated inlets occur when tidal flushing dominates longshore drift. This happens when the tidal prism is large or the longshore drift is weak. The vigorous tidal flushing keeps the inlet free of sand, making it easy to navigate for boats. The channel is relatively stable, remaining in the same position for many years. The vigorous tidal flow also clears out any sand that migrates into the outlet by longshore drift. The large tidal prism produces a large ebb tidal delta, which can be seen several hundred meters offshore and which may be cut by a deep channel cut by the ebb tides. Here's an example of an ebb tidal delta, Johns Pass in Pinellas County, Florida. You can see the ebb tidal delta accumulating outside the inlet and the deeper channel carved by the vigorous tidal currents. The islands inside the inlet are actually flood tidal deltas that have accumulated enough sand to rise above sea level. The inlet at Johns Pass is kept free of sand by vigorous tidal currents. This diagram from a thesis at USF by Tiffany Roberts shows that velocities can exceed 1.3 meters per second or nearly 4 miles per hour. Another example of a tide-dominated inlet is Tampa Bay itself. All of the water flowing in and out of Tampa Bay each tidal cycle, twice per day, makes up its tidal prism and carries vast amounts of sand, even though it is not confined to a narrow channel. The ebb tidal deltas have accumulated so much sand that they have risen above sea level as islands, such as Mullet Key and Egmont Key. A wave-dominated inlet is the exact opposite of a tide-dominated inlet. Now the flow of sand is dominated by longshore drift caused by waves, not tidal currents. This can happen when longshore drift is especially strong or the tidal prism is small, causing the tidal currents to be weak. Regardless, the tidal currents are unable to keep the inlet free of sand and it continuously becomes clogged, forcing it to migrate to pass water. There is no ebb tidal delta because all of the sand carried by the weak tidal currents is swept down the coast by longshore drift. Here's how it works. Longshore drift moves sand into the mouth of the inlet and the tidal currents aren't strong enough to force their way through. This forces the inlet to bypass the new sand by shifting a tiny bit in the downdrift direction. As this process continues, the inlet becomes stretched longer and longer. Eventually, the entrance to the inlet on the lagoon side doesn't match up with the exit from the inlet on the ocean side, and a blind pass is formed. The blind refers to the fact that you can't see through the inlet from the ocean side, so it's hidden. All you would see is land. Here's an example of a wave-dominated blind pass along Florida's west coast, Captiva Pass. The arrow shows the inlet. Notice the absence of an ebb tidal delta and the relatively straight coastline caused by the strong movement of sand via longshore drift. Here's another, the aptly named Blind Pass in Pinellas County. As blind passes migrate, they become more and more inefficient in moving the tidal prism. This is because the water experiences more and more friction as it passes between the lagoon and the sea. But remember, the tidal currents are already weak in a wave-dominated inlet, so this extra friction sometimes puts them on their deathbed. When this happens, a wave-dominated inlet can eventually seal up. The tidal currents become insufficient to force their way through the longshore drift deposited sand, and the inlet just stops. This has happened many times along the Florida coast. Here's an example of a closed wave-dominated inlet. You can see where the water used to go, but the longshore drift was just too strong, or the tidal currents were just too weak to keep the inlet open, and it closed.